Hey there guys, it's Mr. Sheeline here. This is going to be the video for the Check Your Understandings in the Unit 6.1 notes for uniform circular motion. Okay, so this is just going to be the video that covers understanding number 1, number 2, 3, and 4, okay? So this is the stuff before the forces in circular motion, okay? So taking a look here at number 1, a child in a merry-go-round is 4.4 meters from the center of the ride, traveling at a constant speed of 1.8 meters per second. Determine the magnitude of the child's centripetal acceleration. So this is not too bad, really, this question. Ooh, I'm a bit too zoomed in here. Sorry about your ears. Okay. So really not too bad. So remember, our equation here for centripetal acceleration is going to be centripetal acceleration is equal to the tangential velocity squared over the radius. So really, and we've got both things we need here. So looking at the variables that we have here in this problem, well, we've got the child, which is seated 4.4 meters away from the center, so that means that our radius here is 4.4 meters, and the velocity here is 1.8. Now, real quick, how do I know that that's the radius? Well, because we only have one subject here that's on this merry-go-round, it's circular, that's my center, my child is the one we're tracking, so it's the one that's making the circular, motion here. And we'll see problems like this that, because I'm sure your brain may have said, like, well, I don't know where she is in relationship to the entire size of the merry-go-round. When it comes to circular motion, it doesn't matter. Now, what you'll see, though, is that as you increase the distance from the center, as you increase the radius, what you'll see is that it's going to decrease the centripetal acceleration, okay? And we'll get to that later on. But anyway, so it doesn't matter exactly where the girl is sitting, on the merry-go-round. It's just the fact that she is sitting 4.4 meters from the center. That's what we care about. We want to know what her acceleration is here, this distance, and as she's going this rate all the way around it. Okay? So, easy peasy. Let's just plug these in. I mean, it's really not that bad at the beginning. So 1.8 squared divided by 4.4. Okay, well, we plug that into our calculator. So 1.8 squared. So 1.8 squared divided by 4.4, and then that's going to give me 0.74 meters per second squared. Okay. Now remember two things. Centripetal acceleration is not a vector quantity because it's moving in this direction. At any given point, it's moving in this direction. Also, at every point, our velocity has a different direction. So it's a moot point to try to make this a vector quantity. Okay, so, but it is still meters per second squared because we're still talking about, we're still having to describe how quick it is that, why am I blanking here? We're still describing how quick it is that we're moving. And if you are wondering how that works out, how quick the rate is changing towards the center. So, but if you're wondering how these units basically even out, just think of it this way. So here we have meters per second, and down here it's just meters. So the squared will be distributed to the meters and the seconds here, but since there's 2 meters, this one would cancel out, and then this one would just be left with 1 rather than squared, and then you're left with meters per second squared. So that's simply just how it works out, So anyway, so that would be our answer here for Check Your Understanding number 1. So let's take a look here at Check Your Understanding number 2. Check your understanding number 2. So a test car moves at a constant velocity around a circular track. If the car is 48.2 meters from the track center and has a centripetal acceleration of 8.05 meters per second squared, what's the car's tangential velocity? Tangential velocity. Okay, so we have our radius here for our car, which is 48.2 meters. Okay, what else do we have? Well, we have that. We've got the centripetal acceleration, which is 8.05 meters per second squared. And we're wanting to know what the tangential velocity is. Okay, well, cool beans. We'll just write this bad boy down real quick, because that's what we have to work with. And let's just solve for velocity. So when I know I'm going to solve for velocity, I know that my radius is going to move over to here, so it'll become centripetal acceleration multiplied by radius. To get rid of that, we're just going to then square root everything, and then we're ready to go. So velocity will then be equal to 8.05 times 48.2. And let's see what we get. So pop that, 8.05 times 48.2. And I'm going to get here 19.7 meters per second, okay? And the same thing goes here as far as, yes, it is velocity, it's tangential velocity, but it's not, it's a scalar quantity in this case, technically speaking. It's because it changes direction all the time. It's a moot point to talk about what direction it's moving in, all that jazz. So our answer here simply would just be 19.7 meters per second. Okay, so now we're going to be getting into 3 and 4, which 3 and 4 is going to have you practice, it's practicing that period equation, and then also the frequency equation when it comes to centripetal acceleration. So we'll see which one we're going to have to use here in Check Your Understanding number 3. So for Check Your Understanding number 3, find the magnitude and the direction of the centripetal acceleration of a piece of lettuce on the inside of a rotating salad spinner. The spinner has a diameter of 19.4 centimeters and is rotating at 780 RPMs, revolutions per minute. The rotation is clockwise, as viewed from above. At the instant of inspection, the lettuce is moving eastward, okay? Which you'll see that really doesn't matter, okay? Or what you should acknowledge is that it really doesn't matter. All it is just to, sync up with the picture, that's the image that's provided. Okay, so let's just, list out the variables that we have here. So we have a diameter. So we have a diameter of 19.4 centimeters. Okay, that's going to have to change. And it's rotating at 780 RPM. Now, let's just take a second here to kind of think about this for a second. So let's go back and take a look here at period, and let's see if this is the one that we have to use here. So period is the time to complete for one complete trip around the circle. Okay, so that would be to say, so the time it takes for one revolution. So for you to go from here and then to go all the way around and then to go back and then finish where you started, the time it takes, that's your period. Okay, and then let's take a look here at frequency. Okay, so frequency, though, this is something that is now spinning, and it just keeps spinning, and it keeps spinning, and it keeps spinning, and it keeps spinning. But what we're trying to do is to say, let's say, because it started spinning from, this is the point at which it began to spin from, this is where we're keeping our mark. Every time it hits that mark, we count the number of times it does that, and that would be a revolution. And every revolution that it happens within, in this case, what says here a second, that's what it would tell us. There's this many revolutions for every second, for every minute. So, okay, so which one do we want to use here? Which one can we use here? We're given revolutions per minute. So I would say then we're not using period, because the period is the time it takes. So this one would be just straight up like seconds. So it would tell us it was able to make one full revolution in so many seconds. But because the verbiage is revolutions per minute, we want to use frequency. So we're going to be using this equation right here. Now, the only thing that we have to determine, though, is now we have to determine, or we've got to first, before we're able to solve anything, we have to make some conversions. But let's just not get terribly ahead of ourselves here. Let's double check to make sure we don't have any other variables to lock down. So let's see, the rotation is clockwise as we from blah, 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 blah. Okay, and we are asked, let's see here. Yeah, I don't see any other thing that we need to know. So, oh, and there's also pi. Just, I guess, put pi down because we're going to be using pi, obviously. Okay. So let's take a peek at what we have to work with here. So the centripetal acceleration equation is going to be 4 pi squared times the radius times frequency squared. Okay, so this is what we're using. But before we're able to plug anything in, we've got to get our figures matched up here. So remember, the units for centripetal acceleration, the units are meters per second squared. Okay, those are our units right here. And we need to make sure we have units that reflect that right here as well. Okay, so we have to change this twice. Now it's twice because A, it's diameter, and we can't use diameter. We'd have to use here radius. So first we have to change this into radius, and then we have to change this into meters. So let's just make this into our radius. So it'll be radius is equal to, it's just 19.4 divided by 2. So what is that? That's going to be, what, 8, is that 9.7? Yeah, it's 9.7. So it's going to be 9.7 centimeters. Okay, so, and let me just double check that just in case before I get ahead of myself. Okay, yeah, it's 9.7. Now that I've got this out of, or I now have a radius, now I just need to put this in meters. So it's just 1, 2. So 0.097 meters. So there's my radius, 0.097 meters. Okay, now I got to figure out how to get this guy to rather than revolutions per minute, revolutions per second. So this one here, and I'm going to actually use this do this on a different piece of paper. So here is a perfect example where knowing dimensional analysis from chemistry is great, or at least just remembering somewhat to put this together. So we're given revolutions per minute, but we need revolutions per second. And we need that because, again, our units have to be meters per second squared. So 780 here. Now, this is how it would look. Revolutions over 1 minute. Now, the revolutions is just fine. We don't have to mess with that. We've got to change this into seconds. So in order to get rid of this, we're going to put these units up top. So in 1 minute, we've got 60 seconds. And that's it. Minutes would cancel out. We're left with seconds. It'll be whatever, 780 divided by 60 seconds will tell us how many revolutions there are in 1 second. So 780 divided by 60. Oop. And it's going to give us 13. So we're going to have 13 revolutions per second, or you can write 13 revs per second. Either works, but it's 13. Okay. So we'll have 13 revolutions per second. And I think we are good to go. We can move right along to tell what the centripetal acceleration is. So let's just plug all these in. So a lot going on, so I'm going to separate this. So we just plug in what we have here. So centripetal acceleration is equal to 4 times pi squared times the radius, which is 0.097, times the frequency, which is 13. It'll be 13 squared. Okay, so we'll take it nice and easy on our calculator here. So 4 times pi, which pi for me is like right here. If you've never noticed where pi is at, you should know where pi is at, but just in case you forgot, times 0.097 times 13 squared. Oop. And all together now, we should get this. We should have a centripetal acceleration of 647. We're just going to keep it 647 meters per second squared. Okay. And we have our answer. Okay. So that would be our answer for centripetal acceleration. when we're using frequency. Okay. And then number 4. And then number 4 here. Determine the frequency and the period of rotation of an electric fan if a spot at the end of one blade is 15 centimeters from the center and has a centripetal acceleration of 2,370 meters per second squared. So, okay. So we're trying to find the frequency here. We don't know the frequency. That's what we're trying to find. Okay. And it has, let's see, if a spot at the end of a fan blade is 15 centimeters. So that's already our radius. So radius is 15 centimeters. And we have a centripetal acceleration of 2,370 meters per second squared. We're trying to find frequency. So to write out our equation, it's going to be 4 pi square radius frequency squared. So we just have to arrange this to where we are solving for frequency. So, which is going to be, it seems intimidating, but really it's not all that bad. Okay, so we can just simply do this. So we would just go, 4 divided by all this good stuff. Both sides, this cancels out, that cancels out, this cancels out, and we're left with just that. And then it becomes f squared is equal to that divided by this. Okay, and then just find the square root of everything. So it becomes frequency is equal to the square root of the centripetal acceleration divided by 4 times pi squared times radius. Okay. So this will be the formula that we're using here. But before we do that, there is one thing we have to change. We've got to change this to meters. So I'm just going to go 1, 2. And so I actually have 0.15 meters for my radius. Okay, and now I'm ready to plug in. Okay, so frequency is equal to the square root of 2370 over 4 times pi squared times 0.15. Okay, now here it's not difficult, but just be careful when popping this into your calculator. Make sure you're using parentheses correctly and enough, or else you may make a boo-boo pretty. It's pretty easy to make a boo-boo here. Let's see. And we don't want to make boo-boos. Okay, so that should be good. That should be good. And we should have gotten this. So for frequency, okay, so so we have, just looking at units, we have meters per second squared. Well, actually it'd be meters per second squared. Meters per second squared. And then you would have, for your units up here and then down here would be meters. And then this is where your revolutions would come in. Like, how is it revolutions per second? Well, the meters would cancel out. This would cancel. You're left with seconds. Because it's a denominator in the numerator, it will just be put down here. And then how is it that we end up with revolutions? Well, you're being tricked here. Like this equation down here, the 4 pi squared times your radius, all that mumbo jumbo. Like that's pretty much just that's radians. You're calculating radians here. So radians determines the number of full rotations around a circle. And so you're left with basically revolutions. And anyway, so it's kind of a unit that just pops out of nowhere because there is no revolutions up top here. But what's implied is the fact that you are calculating the number of revolutions, per every second. So that's how it does work out. A little vacuous, a bit conceptual, and that I guess not vacuous, but ethereal, I guess would be the better word. But anyway, we popped it in. We've got the right equation. We've got the right things plugged in, and we're left with 20. It'll be 20 revolutions per second, and then we have our frequency. Now, remember. Let's say you are given frequency. Let's say you're given frequency, and in a problem to find centripetal acceleration, you don't have to use the frequency. in order to solve it. If you really want to, realistically speaking, the two equations that we have, these two right here, the centripetal acceleration is 4 pi squared times the radius times this. It's the same thing. It's the same thing as this, right? It's the same thing as this. Okay, now, I never really talked about how these, work out. I do a little bit, but I don't write it out in the notes. But they're the same thing, so what makes the difference here? Well, what makes the difference is the fact that frequency is just equal to 1 over t. And the true is opposite the other way, that t is just equal to 1 over f. Okay? Because again, this is the time, this is the number of revolutions. Number of revolutions, time. Okay? So it's interchangeable. So if you were, say, given frequency, but you're like, man, I don't feel like using this equation, I want to use this. Cool beans, man. Okay, so all you would have to do then is this. In order to substitute t, all you got to do is just put 1 over your frequency, and then that would be your t. Okay, so it's because again, time it's not that they're interchangeable. It's just they're reciprocals here. Okay, that's what they are. So anyway. What's the message here? The message is just don't freak out, when you're like, oh, I know I've gone over period, I know I've gone over frequency, but I don't really remember, like how, oh my goodness. Just take a breath, understand that they're, again, just they are reciprocal pairs here, that frequency is equal to 1 over period is equal to 1 over frequency, okay? And if you panic and you're like, I don't remember which is which, remember, just go back to your notes. It says so right here. The period is the time it takes for a particular position on a circle to complete one trip around said circle. Okay? So this is time per revolution. Okay? Frequency is revolutions per time. Okay? So again, they just don't panic. Okay? So I did have some kids last year that panicked a bit. We're like, I don't remember. I don't know what this is. Don't sweat it, man. It's okay. We're gonna work on it. Okay. So that's all it is. And just always, it's always one of those things. Just be thinking. Are we working with the circle where it's doing this? Where we, we're going and we're timing it and we're saying, okay, boom. Well, that took 8.3 seconds. Okay. So my time would be, or my period would be 8.3 seconds per revolution. Okay. Are we doing that or are we doing this? We're going like, okay, go 1, 2, 3, 4, 5, 6, 7, 8, 9. Are we doing that? Are we, because this would be frequency is equal to 9 revolutions. We'll say per we'll just say that's like 8 seconds. So it's like what frequency is equal to 1.8 something. 9 divided by 8. 1.125 revolutions per second. Okay. So again, nothing to be spooked about. But if you do want me to take some extra time to help you out, really lock in the difference between revolutions per second when we're talking about frequency versus, seconds per revolution for period, let me know. Like, tell me that you need some extra help. That's still pretty fuzzy from different math classes, different science classes. Let me know and I can help you out. And we can figure that out because it is something integral to this set of notes. Okay, we do need to know this. Okay, so anyway, that is the end of that. So anyway, if you guys still have questions, make sure you ask me, get a hold of me. If not, I'll see you guys in the next one.